Chemistry, we're moving on to the third lesson in Unit 7, Advanced Atomic Theory, and this deals with orbitals and subshells. So in earlier units, we used the Bohr model of the atom, which contains simple circular energy levels called orbitals. So we've seen this model of an atom ever since about the second week of school. Now we're going to learn a more advanced model of atomic energy levels in which each orbital is divided into subshells. Sometimes the words orbitals and subshells are used interchangeably, and they're used differently in different books. To me, orbitals mean what's called the principal quantum number, and while we've never used that term, that's what we think of as an orbital. There's a first orbital, that would be hydrogen and helium, and then the second orbital is the second row, and the third orbital is the third row, and so on down the periodic table. And those actually have the name principal quantum number. I don't really use that name a lot, but we're going to call those orbitals just like we always have. Then within them, we're going to divide those orbitals up into subshells. The subshells are labeled S, P, D, F, and have shapes described by mathematical equations. The S, P, D, F subshells must occur in that order. So however you do it, just remember the letters S, P, D, F in that particular order. For example, the fourth row orbital of the periodic table has 4 subshells: 4s, 4p, 4d, and 4f. So that round circle that you see that says 4 on it, it's really broken into 4 different subshells. So the type of orbitals that a row has depends on its row in the periodic table as follows. The first row is only an S subshell. That would be hydrogen and helium. The second row has an S and P subshell. So you'll notice that the first 2 elements in the second row, that would be lithium and beryllium, have a 2s orbital. The elements over to the right, from boron over to neon in the second row, if you look at your periodic table, that would be over in the pink area, they have both a 2s and a 2p orbital. So in fact, they have a 1s orbital, they have a 2s orbital, and they have a 2p orbital. So everything boron, boron, carbon, nitrogen, oxygen, fluorine, and neon have a 1s orbital, they have a 2s orbital, and they have a 2p orbital. Now when we get down to the third row has an S, P, and D orbital. So you can see that the elements sodium and magnesium, Na and Mg, are in the 3s, have a 3s orbital. Then everything over to the right from aluminum over to argon also has a 3p orbital. So argon, for example, has a 1s orbital, it has a 2s orbital, has a 2p orbital, a 3s orbital, and a 3p orbital. That's argon, just to give you one example. Okay, now we go on down to the fourth row. The fourth row has, and everything below, has an S, P, D, and F orbital. Now you notice something funny is that the 3D orbital, which is in yellow there, is down in the fourth row. Why is that? Well, that cannot be the 4D orbital. And why is that? Because remember we said the order has to be S, P, D, and F. So look at the third row. The third row has its 3S. And then you go to the right, it has its 3P. Now you go down below and you have the 4s in the fourth row. Now that D, that first row of D orbitals there in yellow, cannot belong to the fourth row. Why? Because the fourth row has not had its P orbital yet. You go 4s and then you go into that D orbital, that first row of D orbitals in yellow, that can't belong to the fourth row because the order has to be S, P, D, F. So what is the most recent row that has had a p orbital? And that would be the third row. So you see 3s, 3p, then the next one is d. So that d cannot have its d orbital before its p orbital. So you can't go 4s, 4d, 4p. That's what would happen if you went straight across the fourth row. You're not allowed to do that. You're not allowed to have d before p. So the d orbital therefore has to belong to the last row that already has had its p orbital. That would be 3. 3s, 3p, 3d. Now as you go across, you go 4s. Now the 3d orbital is there, and then you go to 4p, and then you go down to 5s. And now that d orbital, that second row of d orbitals, the second row of yellow, cannot belong to the fifth row. There we go. It cannot belong to the fifth row because the fifth row has not had its p orbital yet. So you can't go 5s, 5d, 5p. That's illegal. So that d orbital that says 4d has to belong to the fourth row because the fourth row has had its p orbital already, and it has to go s, p, d, f. It has to be in that order. So that's the reason why the d orbitals are one row below where they seem like they should be, because d has to come after p. Alright, now as you get down even deeper, down into the 6th and 7th, you get the f orbitals, and we don't talk about those a whole lot, but everything down below that has an f orbital. And the largest element in nature is uranium, number 92, which is down in that bottom row of the green orbital. That's the f orbital, or f subshell, I should say. So that's going to be in the 5f subshell, and that's the largest element in the universe that we know of. So each row of the periodic table must fill its subshell in the order S, P, D, F. And by the way, let's pause for a minute. You now see another reason why the periodic table has the shape it does. If you were to just look at it and never having seen it before, and you said, kind of identify 4 major sections of the periodic table, you'd look at the 2 columns on the left, the ones in gray, they kind of stick up. And then the yellow, the transition metals in the middle, they're kind of in a valley there. And then the pink over on the right, they kind of stick up. And then the F's down below, they have their own space down there. And so this is why the periodic table is shaped and organized the way it is, one of the many reasons, and that is because it outlines, it defines where the S, P, D, and F orbitals are. And again, I say orbitals, I might use it interchangeably with subshells, but these are really subshells as the way that I like to use them. So first row. So the first row elements, hydrogen and helium, place an electron in the 1s subshell. After the first row, all s subshell elements are alkali and alkaline earth metals in the first 2 columns. So the first 2 columns are the s subshells. The only exception being the first row, where helium is considered to have an S subshell even though it's way over to the right-hand side of the periodic table. Each row of the periodic table must fill its subshell in the order S, P, D, and F. So in the second row, the first 2 elements in the second row, lithium and beryllium, place 2 electrons in the 2s subshell first. When the S subshell is filled, the next 6 elements, boron, carbon, nitrogen, oxygen, fluorine, and neon, those are in the pink over in that red box and the pink over on the right where it says 2p. They place electrons in the P subshell, which has a slightly higher energy than the S subshell. So that's the difference. We've always treated it just like second orbital, but we see that it has really 2 sections. One that's a little bit lower energy, the 2s, one that's a little bit higher energy, and that's the 2p. So each row of the periodic table must fill its subshells in the order S, P, D, F. So let's look at the third row. Sodium and magnesium go in the 3s subshell. Aluminum, silicon, phosphorus, sulfur, chlorine, and argon place electrons in the 3p subshell. Next comes the third orbital d subshell. Since the 3p subshell must come before the 3d, the 3d is placed in the fourth row. Again, that 3d cannot be the 4d. If you went 4s, 4d, 4p, that would be illegal, because the D cannot come before the P. Therefore, that D has to belong to the third row. So 3S, 3P, 3D. D subshells, transition metals, are always placed one row below their row number. That's all you have to remember, okay? Just remember that fact. Each row of the periodic table must fill its subshells in the order S, P, D, and F. So the fourth row. So now you have a 4s, then you go over to the 4p. Now you go down to the 4d. So K and Ca electrons go in the S subshell. Ga, Ge, As, Se, Br, Kr place electrons in the P subshell. Next comes the fourth orbital D subshell, which is placed down in the fifth row. The fourth orbital also has an F subshell placed in the sixth row. The periodic table breaks out the 4F, called the lanthanide series, down below. So the first row has one S, has an S subshell only. The second row has an S and a P. The third row has an S, a P, and a D. And from the fourth row on down, you have an S, a P, a D, and an F. The D orbital, the 4D orbital, goes one row below the fourth row, and the 4F orbital goes two rows below the fourth row. You see it's down there in the sixth row. The 4F subshell is two rows below the fourth row. It appears in the sixth row. Each row of the periodic table must fill its subshells in the order S, P, D, F. Okay, keep repeating that because you got to remember that order. The fifth row, R, B, rubidium and strontium electrons go in the 5s subshell, and then In, Sn, Sp, Te, I, Xe place electrons in the 5p subshell. Next comes the fifth orbital D subshell placed in the sixth row. And the fifth orbital has a 5f subshell placed in the seventh row called the actinide series. And it is in the actinide series where you find the largest natural element, uranium. The 5f subshell is placed in the seventh row. Now we're going to get into the shapes of these subshells, and they're very unusual. Okay, we've talked about just these circular orbitals up until now, but you're going to find that they have some very unusual shapes. So the subshells have unusual shapes that were determined mathematically by physicist Erwin Schrödinger from his equation known as Schrödinger's equation. All you need to know about Schrödinger's equation is that the shapes of the subshells indicate the probability that an electron will be found in a particular location. So Schrödinger's equation, Schrödinger's electron density distribution of the hydrogen electron, and that is called psi squared, is called the wave function. The wave function gives the probability that an electron will be in a specific location. Darker blue means higher probability. So there's an example of an s orbital. It could be a 1s, a 2s, a 3s. The s orbitals are spherical in shape. Okay, so we're not thinking of circles, we're thinking 3 dimensions. So the electron is most likely to be found very close to the center of the x, y, and z axes. That would be the nucleus of the atom. It's less likely to be found farther out, and that's why the blue becomes lighter and lighter and more spread out as you get away from the nucleus of the atom. The shapes of the subshells are shown on the following slides. So S, subshell. The S stands for spherical. So you see there's the 1s, there's the 2s, and there's the 3s. What you notice about them is the 1s is what you'd expect it to look like. The electron is most likely to be found. It's more dense. The density is greatest when you're closer to the nucleus. Now when you go to 2s, what you see is the electron can be farther away. That's a higher energy level. They're both spherical, but the 2s is electrons with higher energy. And another strange thing that you don't really have to understand why, just understand that it is that it has what are called nodes. Notice that there's darker blue near the center of that axis there, and then it gets lighter, and then as you get out farther away, there's a circle that's darker again. So the electron actually has a greater probability of being found in that darker circle away from the 2s than it does in that lighter area closer in. And for the 3s, it has 3 that are called nodes. The one in the center you see is very dark. Then you see a circle that's a little bit darker away from that. And then you see another circle farther out that's a little bit darker. So it's as though there's kind of energy levels within that s orbital. And the electron is most likely to be in those places where you see it darker. You don't have to understand why, you just have to understand that's the way it is. So the S subshell is spherical. The diagram on the right shows the 1s, 2s, and 3s subshells. All 3 are spherical. In the 2s and 3s subshells, there are lighter and darker regions. The lighter areas are called nodes. Nodes are locations where electrons are less likely to be found. So the 2s has 2 areas of high electron density separated by a node. You can see it's pointing to that. The node is the lighter area where it's less likely to be found, and then there's the areas of higher probability of finding an electron. For the 3s, you can see that there are 2 nodes, and there are 3 areas of high electron density, higher probability. So the 3s orbital has 3 areas of high electron density separated by 2 nodes. The p orbitals, the p subshells I should say. The mnemonic is potato because they're shaped kind of like potatoes. Some people say they're shaped like balloons or bowling pins or something like that. But we're going to say potatoes because it starts with P, and this is called the P subshell. The P subshell is further broken into 3 sections: PX, PY, and PZ. Each of the 3 sections is divided into 2 lobes. And the lobes are the potato shapes that you see there. So when you look at the X, the first one, the PX, those 2 lobes are part of the same orbital. They look like they're 2 different places, but they're part of the same orbital. They're part of the PX. So if an electron is in the PX subshell, it can be in either one of those lobes. There's no rule for why it would be on one side rather than the other. It can be in either one of those. If they're in the PY orbital, they can be in either one of the lobes that you see along the y-axis. And if they're in the PZ orbital, they can be in either of the lobes that you see along the z-axis. When you put them all together, you can see how they expand each way on each axis. In between the blue lobes are nodes where electrons do not reside. And that would be right where the nucleus is, right in the center of the atom, right there. Now the question is, can they get from one lobe across to the other one? And the answer is they can. How they do that is one of the mysteries of nature that you don't need to understand. But in the PX orbital, or subshells we'd like to call it, they can go from the left side to the right side, even though in between the left and the right there's an area where they're not supposed to be able to go. They can get over there somehow. You don't need to understand why. Each P section, PX, PY, PZ, is aligned along an axis. The P subshells in the 3rd, 4th, and later orbitals have identical shapes to the 2P. So the 3P has shape exactly like this. 4P shape exactly like this. They're just bigger and further away from the nucleus. So P subshell So each of the elements in the pink square contribute 1 electron to the p subshell. So the second row, for example, the second orbital can hold 8 electrons. We've said that for a long time. The 2s holds 2 of those 8 electrons, and the 2p holds 6 of them. Same with the third row. The 3s holds 2 electrons, the 3p holds 6 electrons. For example, the second row contains boron, carbon, nitrogen, oxygen, fluorine, and neon. Each element adds 1 electron for a total of 6 electrons. The electrons are added in the following order. First, they're added to the 2px orbital. Then one is added to the 2py orbital. And then one is added to the 2pz orbital. Then the fourth electron goes back to the 2px orbital. And then the fifth one goes to the 2py orbital, and the sixth one goes to the 2pz orbital. Now you might think, and I thought this when I was learning this, that each electron goes into one of those lobes. So you notice that in the x, y, and z orbitals, there's a total of 6 lobes. 2 in the px, 2 in the py, and 2 in the pz. You might think that each of those lobes gets one of those 6 electrons. It's not true. In the px, for example, there's going to be 2 electrons, up to 2 electrons. They could both be on the lobe on the right, or they could both be in the lobe on the left. It doesn't have to do with one lobe, one electron. It doesn't work that way. This order will become clear later in this lesson. So how many electrons can fluorine hold, and where are they located? Fluorine has an atomic number of 9, so it has 9 electrons in its natural state. The first 2 electrons fill the 1s orbital, so they're buzzing around in that spherical shaped orbital very close to the nucleus. The second 2 electrons fill the 2s orbital. So they are buzzing around in a little bit bigger sphere. But you'll notice something. The 2 spheres overlap. Even though the 2s is bigger than the 1s, the electrons in the 2s can still get very close to the nucleus. So it's possible for the electrons in the 2s, they do travel about randomly, it's possible for them, for an electron in the 2s to be closer to the nucleus than an electron in the 1s. Not permanently, but just for a split second while they're flying around. So those 2s orbitals can go very close to the nucleus, just as the 1s orbitals can. It's just that the 2s electrons have the ability, because they have more energy, to go farther away from the nucleus. Okay, the final 5 electrons fill the 2p orbital in the order px1, and then the second one goes to the py1, the third one goes to the pz1, the fourth one goes back to the x, the px, and that's px2, and the fifth one goes to py2. So you see them there. Now the way I did draw them there is it looks like that each of those lobes gets 1 electron. But again, the x, for example, the 2 electrons in the px, they could both be on the same side, on the left or on the right. They don't have to be in separate lobes. They just don't. So it may appear that each lobe receives 1 electron, but this is not correct. All we know is that the 2px subshell, for example, has 2 electrons somewhere. They could both be in the same lobe or different lobes. So now we're going to the D subshell, and the mnemonic is donut. And there's the D subshell. Looks kind of crazy. And we use the mnemonic donut because you can see that one of those subshells does have a torus shape, which is a donut shape. So the D orbital has 5 subshells. Each subshell can hold 2 electrons for up to a total up to 10 electrons in the D orbital. So you notice that there's a lot more than 10 lobes there. Yet only 10 electrons can be held. So that shows you that each lobe does not hold an electron. That's not the case. Okay, so this is a little bit challenging to learn. So the first one is called the DYZ, and its lobes are in between the Y and the Z axes. You can see that in the upper left. The DXY, the lobes are in between the X and the Y axes. And the DXZ, the lobes are in between the X and the Z axes. So those three are kind of easy to remember. Then there's the DZ squared. Now this has nothing to do with math. It's just a notation that's used. The DZ squared is the one with the donut, and the lobes go up and down along the Z axis. And then we have the DX squared minus Y squared, and that has 4 lobes. 2 of them go along the X axis and 2 of them go along the Y axis, okay? So the DXY, XZ, and YZ are oriented, pointed in between these axes. The DZ squared is oriented along the Z axis with the donut intersecting the X and Y axes. And the DX squared minus Y squared orbital has lobes pointing along the X and Y axes. The d orbitals represent electrons added by the transition metals. So if you count the transition metals alone, you'll notice there's 10 transition metals in each row. The 3d row has 10, the 4d has 10, and so forth. So those are the 10 electrons that are contributed there. Only s and p orbital electrons can be valence electrons. D orbital electrons are never valence electrons. You don't need to understand why, just remember that fact. Okay, why is the 3D subshell in the 4th row? Remember, subshells must be in the following order: S, P, D, and F. The D subshell represents the transition metals, and the first one we encounter is in the 4th row. If it were referred to as the 4D subshell, then the order of the 4th row subshells would be 4S, 4D, 4P. This violates the order of S, P, D. Since the 3rd row has already had its 3S and 3P subshells earlier, then this D subshell must belong to the 3rd row, not the 4th row. So illegal: 4S, 4D, 4P. Legal: 4S, 3D, because the 3rd row has already had its p orbital, and 4P. And then the F subshell, we're going to talk about that almost not at all, but it has 7 different subshells within the F subshell. Each section can hold 2 electrons for a total of 14 electrons in the F orbital or F subshell. You do not need to remember the names or exact shapes of the F orbitals. As with the D orbital, F orbital electrons cannot be valence electrons. So the F orbital represents the elements in the lanthanide and actinide series elements at the bottom of the periodic table, and if you count the number of squares in each of those rows, there's 14. So that's why that orbital can hold 14 electrons. Textbooks disagree on where the 4F and 5F orbitals begin. According to your textbook, the 4F subshell begins immediately after the 6S subshell. This would make element 57, lanthanum, the first element in the 4F subshell, and it would go there, where you see here. According to other textbooks, the diagram below, the 4F subshell begins after the first element in the 5D subshell, and that's lanthanum, element 57. This would make element 58, cerium, the first element in the 4F subshell. I'm just stating this as a note. Don't worry about it. We're hardly going to talk about the F subshells at all. So who's right? Who cares? If textbooks can't agree, then you won't be responsible. All right, and that takes care of our lecture on orbitals and subshells. It's a lot to absorb, but just like anything else, repetition, and it will come through for you.